Okay, continuing on with Chapter 11 problems. Here's number 43. So it's hard to see, but there's two ice skaters. There's one ice skater here, one ice skater here. This one's carrying a rod, and they're going towards each other, and then they're going to both grab onto the rod, and they're going to start to rotate around in a circle like this. We have their masses, and their paths are separated by 3 meters. So that's 3 meters from there to there. Opposite velocities of 1.4 meters per second each, and they rotate around the center of the pole, and we're going to assume that there's no friction. What's the radius of the circle? Well, that's pretty easy. That's just 1.5 meters, so don't really need to do much there. R is 1.5 meters. What's the angular speed of the skaters and the kinetic energy of the two skater system? So the angular speed of the skaters. So there's kind of a couple ways to think about this. If you look at my solutions, in my solutions I just say, oh, well, the angular speed is just their tangential speed divided by r. So this kind of makes sense in some ways because this is sort of the relationship right here. It's like they're going in a straight line, but they still have an angular speed about a particular point. It's kind of an interesting thing to think about. Like you can just have an object that's going in a straight line, and you might not think it has any angular speed because it's not going around a circle. But if I had it relative to like a pivot point right there, I could say that the angular speed of this thing about this point is v over r, the angular speed about that point. So that's the way that we can think about that. You can also kind of derive that from conservation of angular momentum, but this works out for this problem that the angular speed is just v over r. So that's pretty easy to do. What's the kinetic energy of the two skater system? So I think that we can do this a couple of different ways. The way that I did it in my solutions was by doing rotational kinetic energy. So because they're rotating around the center, I'm wondering if we can do it by translational kinetic energy as well, but I don't think so because I think they're going to lose some energy when they start to rotate around. So as far as the energy goes, we're going to have a rotational kinetic energy that's just 1/2 I omega squared. We know the omega because we already figured that out. We just have to figure out the moment of inertia. And the moment of inertia for objects, instead of a solid thing, if it's just two objects, we're going to add up. Oops, that's a sum. That was a terrible sigma. Let's do that again. We're going to add up the mr squareds. Ah, there's an r in there. There we go. And I have the masses. So there's the mass, and then the radius is 1.5, and there's 2 of them. So this is going to be 2 times the mass times the radius squared, since I'll have 2 skaters inside of there. And then I'll get a number for my kinetic energy. You can work that out. You can solve it out. Let's see. So, you have to, whatever you get for here is going to get plugged into there, and whatever you get for here is going to get plugged in there, and you'll figure out the kinetic energy. So then it says, next the skaters pull along the pole until they're separated by 1 meter. What's their angular speed? And then the kinetic energy of the system. So this time we definitely have to use a conservation of angular momentum. So we're going to have an L initial equals an L final. And then this is kind of a strange situation because we have their I together, their moment of inertia together, times their initial angular velocity, and that's I times their final angular velocity. And if you look at this, it's like, well, why would omega f be different than omega I? It's because the i's change over here. So you have a system where you have it's almost like the mass of the system changes. And in a translational problem, a collision problem where you have like one mass going and colliding with another mass, usually their masses don't change, right? But in this situation, the mass does change. So what I might write is I might write an initial moment of inertia and a final moment of inertia over there. I already know the initial moment of inertia and the initial angular speed because we figured it out over here. The final moment of inertia is just going to be recalculating down here. I final is just going to be the sum of the mr squareds again, but the r is going to be different. So you'll just plug in a different r value over here. Once again, it's going to be 2m, and then they're separated by 1 meter. So then it's going to be 1 squared inside there. And then the m is just the mass that they're given up here, 50 kilograms. So that'll be 2 times 50 times 1 squared. So that's 100 for this I, whatever it is you got for the other I, and then you can figure out what the angular velocity is right there. Okay, so then the kinetic energy of the system. So then we're just going back once again and using this formula, the new kinetic energy with a new moment of inertia and a new angular velocity. And then it's going to turn out that their kinetic energy is going to increase And the source of that increase in kinetic energy is going to be because they had to pull themselves in. So they had to do work in order to pull themselves along this axis right here to pull themselves closer together. And that's where the new kinetic energy comes from. Okay, so there you go. Look at my solutions and you can figure out the rest of the problem too. Okay, moving on to 45. Let's see here. Is there a diagram with this one? No diagram. Okay, so a man stands on a platform that's rotating without friction. Oh yeah, okay, and then he's got an angular speed. His arms are outstretched. He holds a brick in each hand. Oh, that's so nice. They give you the rotational of inertia. So they give you what the I is. So it's like there's going to be an I initial, and then there's going to be an I final. And this is going to be conservation of angular momentum. So they give you his initial moment of inertia, and then they give you the final moment of inertia. So that's super easy. What's the resulting angular speed of the platform and the ratio of the kinetic energies, and what provided the additional kinetic energy? So we're looking for, in part A right here, the resulting angular speed of the platform, the man and the platform altogether. So we have just conservation of angular momentum. Li equals Lf, and then similar to what we did up here, we're going to have I initial times omega initial equals I final times omega final. That's given, that's given, that's given, and then you can solve for this. So that's actually pretty easy to do. Now, one thing is that they're given everything in revolutions per second. So you could get your omega final in revolutions per second, which would be fine. And that's an okay way to do it. But if you do the problem and find out the kinetic energies, you know, looking at my solutions, I leave everything in revolutions per second. So here's the thing. If you're looking for the ratio of the new kinetic energy to the original kinetic energy, that's going to be K final over K initial. If I'm looking for just the value of one of these or the other, I can't use revolutions per second. I have to turn it into radians per second. But because I'm doing a ratio, those units are going to cancel out, and I'll be fine doing it in terms of revolutions per second instead of radians per second. So once again, if you're looking for the actual value for Kf or Ki, then you need to use radians per second. But because I'm doing a ratio, those units are going to cancel out. It's basically, if you think about how I would get from revolutions per second to radians per second, if I have revolutions per second, I'm going to multiply it by 2 pi radians per revolution, and right, so 2 pi radians is 1 revolution. I would cancel that out, and I'd get a factor of 2 pi, but that 2 pi is going to go in the numerator and the denominator over here, so it'll sort of cancel out. So in order to figure out these, this is actually pretty easy. My final, this is going to be 1/2 I final times my final kinetic energy squared, and this is going to be 1/2 I initial times my initial energy squared, and you'll get a number for that. And then it says what source provided the, so this is going to be a ratio that's bigger than 1. So the final kinetic energy is more than the initial kinetic energy. And the source of that kinetic energy is because the man had to pull his arms in and do work on the bricks as he pulled his arms in. Okay, moving right along. There's a lot going on here. So let's move on to 53. Okay, so we have a thin rod of length 5 meters, can rotate about the center axis right here. And then there's a bullet, 3-gram bullet. Probably want to change that to kilograms since this is in meters. It's nice to do things in kilograms. The view from above, the bullet takes this path. The bullet lodges in the rod. The angular velocity is this after the collision. What's the bullet speed just before impact? Yeah, so this is pretty doable. This is a conservation of angular momentum idea. So we have the initial angular momentum is going to be the final angular momentum. The initial angular momentum over here is just that of the bullet. So that's just an object by itself, mvr sine theta. So that's here, mvr sine theta. This r right here is not the radius of this whole thing. Oh yeah, actually there's going to be an r over here. I guess they'll sort of end up being the same r. So this bullet ends up lodging in the edge over here, so that r is going to be the same. But once again, we can say this is mvr perpendicular. If I just, this is going to be pretty interesting to do, but how do I get the perpendicular distance back here? So I got to take this path right here, and I got to figure out where along the path, it's going to be perpendicular from the axis to this point right here. And I could take this as my r perpendicular right here, which that looks like a pain because I don't know what that answer is. So let's not do it that way. Let's just do mvr sine theta right here. And I think I did this maybe slightly wrong in my solution. So if this is my vector r, and then my vector v is going like this, I need to put them tail to tail. So I have to have r like this, and then v like this, and then I have to find out the angle between them. And I think that that's the same angle here as this angle here, so it's going to work out. So I can just do mvr sine theta. Okay, so sorry to have to take you through that. Just working things out in my head as I'm going along here. Coming back up here, the final angular momentum over here. So I'm going to have the I of the rod plus the I of the bullet times the final speed of the system. So I'm actually looking for this V right here. I'm given the mass of the bullet. Make sure that turns into kilograms. I know my r sine theta because I know this distance r right here. It's 0.5 meters for the whole length. So this r is going to be 0.25 meters. And then the I for the rod. So I don't think it's given in the problem, and I didn't put it on here, and I will give it to you on a test or something. So the I for the rod is going to be 1/12 ml squared, where that's the whole length of the rod and that's the mass of the rod. The I for the bullet is going to be just mr squared, just like that. So now we have everything that we need. We have the mass, we have r, we have this mass, we have this L, we have this 1/12, and so we're just solving for V right here. So just plug a bunch of things in and solve for V. I think that in my calculations, I put things in terms of L. So if you want to have L is 2R or R is L over 2, that's an R, then you could start to cancel some things out in here if you wanted to. So I could put in R over 2 there, and then I'd have a bunch of things with R in it, and the R's would cancel. Or just plug in the numbers if you want to. And that's it, then you'll find V. Okay, here we are, last problem. All right, great. So last problem, we have a collision type of problem. So we have this uniform rod, and it rotates in this plane. Cool, they give you the moment of inertia. That's so nice. You don't have to figure out the moment of inertia. We have the mass and the length of this as the rod, so it's going to swing down this way. And as it swings through its lowest position, it collides with this putty that sticks to the end of the rod. The angular speed is 2.4 before the speed. What's the angular speed after the collision? So it's just a collision problem, but it's an angular momentum problem. So once again, we're going to start it with Li equals Lf. It's conservation of angular momentum. The angular momentum before is going to be the moment of inertia of the rod times the initial speed, which they give you. And then over on this side, we're going to get the moment of inertia of the rod plus the moment of inertia of the putty, I guess, times the final speed. And then we have, what else do we have here? I think that's it. We have all the information that we need. It's just figuring out the moment of inertia of the rod, which is given right there. And then the moment of inertia of the putty is just going to be m times r squared. So you have this mass and we have this radius right there. And then we're just looking for the final angular momentum. So that's actually a pretty easy problem to do. I did it in my solutions. I kind of manipulated the variables and then I was solving for this. So anyways, that's not so hard. Okay, hopefully these videos were helpful, and if you have questions, you can come ask me.